Everyone, today we have Shiva visiting us from CMU, and he's going to talk to us about statistical optimal transport. So let's all welcome him.
Yeah, great. Thank you. Thank you for the invitation. Okay, so let me just get started. So first of all, let me thank my collaborators. So Tudor is a grad student who worked with Larry and me. He's now a postdoc at MIT. He's amazing. You should try to hire him. He'll be on the job market in, I guess, a year. And everything I'll talk about will also be joint work with Larry and John Reed, who's at Quran. Okay, so let me just get started. First, some very high level motivation for the things that we're going to be talking about. So the talk today will be about optimal transport. I'll ease you into it. I'll tell you a little bit about what it is. But at a high level, it's some subfield that arose in the intersection of operations research and pure math. The framework of optimal transport yields a bunch of things, which are distances to ways to measure distances between distributions, ways to map from one distribution to another. And these things have turned out to be extraordinarily useful in machine learning and statistics. And they're just useful as tools to analyze data. And so as a result, lots of people have gotten interested in these. And maybe arguably, to use these tools more seriously in scientific applications, we need some better understanding of the statistical foundation. So by which I mean ways of saying how well are we estimating various objects in this framework, how can we quantify our uncertainty, and so on. And so that area that focuses on that set of questions is the area of statistical optimal transport. And today's talk will I'll introduce you to some problems in that area and tell you a little bit about them. And maybe as a theorist, the thing that gets me most excited about this is that in contrast to some of the problems that we're all familiar with, understanding these challenges or addressing them requires learning about a bunch of new areas. So in particular, optimal transport has some very large intersection with the theory of partial differential equations and convex analysis, and you'll see why these things come up a lot in this video. Okay, and yeah, feel free to interrupt me at any point with questions of any sort. All right, so let's get going. Okay, so first let me tell you what the problem of transport is. So here's the setting. I'm going to hand to you two distributions P and Q. And the question that the task I'm going to give you is to construct a map which maps the distribution P to the distribution Q. So the picture you should have in mind for the top is somehow I describe to you these two distributions. Maybe the distribution P is some bumpy distribution, the distribution Q is uniform. And what I would like you to do is somehow construct the map on the right. So what is the map on the right telling you? Roughly, it's saying wherever there are regions of high density, if you want to get to uniform, you should push some mass out. And then wherever there are regions of low density, you should push some mass in. And if you followed this mapping in some sense, then you would push this distribution to this one. So this is roughly the picture you should have in mind. We're trying to understand this map. Maybe slightly more formally, a transport map is just something which, if I give you a sample from P and I pass it through this transport map T, then I will obtain a sample from the distribution Q. So I would like you to construct a map T that has this property that if I give it as input something which has distribution P, it will produce for me as output something which has distribution Q. Okay. And throughout, we'll use this standard notation to denote such maps. The map T pushes forward the distribution P onto the distribution Q. Okay. Everyone okay so far? Okay. So now you can say, okay, which transport map do I really want? And the history of this question, it goes back to the 1700s. It was first roughly asked in this form by Gaspard. And so he said, okay, there are potentially many such maps, and what you should do is the following thing. You should specify what is called a cost. A cost is how much does it cost me to move something from a point X to a point T of X, right? So my transport map is going to do this movement for me. I will assign to it some cost. And for now, you should think of something like the distance between X and T of X as the cost. And then you should find, so okay, this is a cost for moving one point to another. And you can ask for a transport map which has smallest expected cost. So this is what the problem he formulated was, that you should define this thing. It's called the optimal transport map. It is the transport map. So it's a valid transport map in the sense that it pushes P onto Q. and it has minimum cost, minimum expected cost. So this cost you should think of as I'm taking points x and moving them to t of x, so what is the cost of that displacement? Throughout this talk, we'll focus on the squared Euclidean cost. So you should think of the following problem. I would like to identify this map or understand this map, T0, which is a map that pushes P onto Q that has expected squared displacement, which is smallest. It'll turn out, so Gaspard Monge formulated this problem in the 1700s, and then 200 years went by, and there's very little progress on understanding this question. And the reason is, we'll look at it again at some point, but this problem, it's an optimization problem. And even if the cost is very nice, so something like the squared Euclidean distance, it's not clear that this optimization problem has any solutions at all. It's not even clear when transport maps exist. So you should imagine in your head the case where the distribution P has 1 point mass and the distribution Q has 2 point masses. Then there's no way, unless you're allowed to somehow split point masses, that there's no way to map from P to Q. So in some cases, this formulation, this asking for transport maps, may not be a reasonable thing. There may not be any solutions to this problem. And even if you ignore that problem, then the second thing that will be annoying about this optimization problem is that it has an extremely nonlinear constraint. So this benign looking constraint which says that P has to be pushed onto Q by this map, if you think about it, it's encoding for you a change of variables formula. It's saying that if you think of this map as somehow differentiable, then it's saying that for every x, T of x has to be equal to Q of T of x times some Jacobian term. And so there's a very nonlinear constraint that's hiding over here. This makes this optimization problem kind of hard to think about. Okay.
So can T has to be non-random?
Yeah, exactly. Yeah, so that's how, so in the application that Monge cared about, he was thinking about transporting goods from one place to another. And then it doesn't make sense to say, take your good, divide it in two and send half of it here and there. So he had some economics application in mind where it didn't really make sense to think of this as somehow being. When I phrase it as distributions, maybe it's natural to think of randomized terms. Okay, so, okay, so 200 years after that, Kantorovich revisited this problem. He maybe didn't really know about Monge's work, but he formulated a version of this problem that is in some sense much nicer. So he said exactly what Jacob was suggesting, which is rather than think about these maps as being these deterministic maps, you think about what are called transport plans. So a transport plan is just a coupling. So it's a way of coupling distribution P and Q. What is a coupling? It just means it's a joint distribution on P and Q, which has marginal on, say, the x marginal is the distribution P and the y marginal is the distribution Q. How should you interpret a coupling? You should interpret it as saying, I will draw an x and then I will sample a y from the conditional of this coupling, right? So this joint distribution specifies for me some way of moving mass from x to y. The way that I will move mass is I will sample an x and then I will sample from the conditional of this pi quantity to tell me where to go. And it is in some sense a randomized path. Okay, and so you should think about this as every coupling induces a potentially randomized transport plan. And now you can define, again, just as Monge did, you could define the optimal coupling. Right? And so that is, you could say, give me a coupling that minimizes the expected cost. So now I'm imagining drawing x and y from this joint distribution and looking at how far the distance between x and y is. This is a relaxation of Monge's problem. So if I have in my hand a transport map, so a map is a thing that maps x to t of x. Every map has this property. So it induces a coupling. The coupling is just take x and map it to t of x. That is a valid coupling. So in some sense, you have now just enlarged the space of possibilities. You're allowing these randomized maps as well. What is nice about this formulation is, first of all, there's always a solution. There's always a way, there's always at least one coupling. The so-called independent coupling is a valid coupling. I can just say, draw an independent sample from x and an independent sample from y. That's a joint distribution which has marginal p and q. So there's always at least one solution to this optimization problem. But more importantly, and somewhat fundamentally, this is now a linear program. It's potentially infinite dimensional. If you think about it as all of these constraints are now just this pi xy specifying some joint distribution. The constraints are just saying, imagine it's a big matrix. says something about the row sums being P, the column sums being Q. And the cost is just the sum of pi xy times this squared distance. Right? So it's a linear program in this pi quantity. And so as a result, you can use things like duality and so on to study this program. Everyone good so far? Okay. And maybe again, from a practical standpoint, you should think that a transport map is somehow potentially more interpretable and often more useful than a couplet. So at the very least, we'd like to know when maps exist. And this came about from this paper of Jan Brenge. This was also in this fairly recently. And he proved a theorem which essentially says when these two viewpoints are somehow identical. And it basically tells you the following thing. If P is absolutely continuous, that is, it's not just a single point mass, for instance, then there's a unique solution to Monge's program, call it T0. And that unique solution is the gradient of a convex function. So there's some nice properties that that solution has. And also, Kantorovich's program, which is this nice linear program, also has a unique solution. And its unique solution just encodes for you this unique transport map. So as long as you make this single assumption that the distribution P is absolutely continuous, then you're in good shape. There is a unique solution to Monge's program. It's exactly the same as the solution to Kantorovich's program. Everyone's good so far?
So this says nothing about Q, just like puts assumptions on.
Yeah, so as long as you should think of the only obstruction is the one I described, which is P has 1 point, Q has 2 points. As long as you don't have that problem, you're in good shape. Okay, so what is this telling you under this very mild looking assumption? You can have the best of both worlds. This optimal transport problem is kind of nice in many ways. And maybe for some intuition, there's this fact that the map will always be the gradient of a convex function. And this is encoding for you some sort of monotonicity. So if you think about in 1D, the gradient of a convex function is an increasing function. So it's just telling you that your map will never take a point from here and move it there and then move some other point to cross over. Right? So it will never do something suboptimal in some sense. Right? So if your map has there's some sense in which the map doesn't cross itself. And if you remember that figure that I showed you an optimal transport map, and you can sort of see that the lines never crisscross. And that's just a nice property that this map has. This quantity phi0 might come up again. It's called the Brenge potential. So the gradient of the Brenge potential is the transport map. Everyone good so far? Great. Okay, so what is the Wasserstein distance? The optimal value of Kantorovich's program is called the Wasserstein distance. So if I said, I don't care about what the coupling is, I care about what the cost of that coupling is, that in fact defines the distance between distributions. And that distance is called the Wasserstein distance. So if you put some other cost here, you could get other Wasserstein distances. But for us, we'll just care about the squared cost, in which case the distance is the squared Wasserstein distance. So there's the map or the coupling, and then there's the cost of the coupling. The cost of the coupling is a distance between distributions, and it's called the Wasserstein distance. And under the conditions of Brenge's theorem, you can just write it in this different way. And maybe this is a place to pause and think about what is this whole framework doing for you. It's doing something very powerful. It is giving you a way to take somehow a distance between points. So you had in your head this squared Euclidean cost and lift it up in some optimal way to a distance between distributions. Right? So if I provide for you any cost, I give you a metric, then optimal transport will tell you how to define a corresponding metric on the space of distributions of that space. And this is just a nice thing. And this metric, the Wasserstein distance, will inherit some nice features of the underlying metric that you use to define. Right, so let's talk for one more minute about the features of this distance. So you should contrast in your head the Wasserstein distance to other notions of distance like the KL or the chi-square or things that we see often in physics. So that's in which, compared to these, it's very non-brittle. And it's because it inherits some of the features of the underlying Euclidean metric. So some ways to see that it's not a very brittle metric is that it's well defined even between a discrete and a continuous distribution. So there's nothing that says that, so the KL, for example, would be infinite in some ways if you looked at it, or the TB would be 1 if I tried to define it between a discrete and a continuous thing. The Wasserstein is completely sensible even in the setting. Under relatively mild conditions, the empirical measure, so suppose I draw n samples from a distribution and I looked at the Wasserstein distance between the empirical measure and the true distribution. So one of them is discrete, one of them is continuous. This thing would go to 0. And what this tells you is that you can somehow solve some tasks like two sample testing or density estimation and so on. Often you can do so without any smoothing. So this is again a nice feature of the Wasserstein distance. And this in turn is just useful in applications where you're trying to minimize the distance. So GANs or Wasserstein GANs, for example, they try to construct some maps that minimizes some notion of the Wasserstein distance. It's just convenient that you don't have to do smoothing in order to understand this distance. Another nice feature of the Wasserstein distance is that averages and barycenters. So if I take a bunch of distributions and say, what is their midpoint? It'll have some different behavior than the Euclidean midpoint of these distributions, and it will be in some sense more geometrically intuitive. And so here's the picture you should keep in mind. It's probably easier to understand what's going on in the picture on the right. So suppose I gave you these two distributions. They're the orange Gaussian and the blue Gaussian. And I said, what is their midpoint? You could try to say, what is their Euclidean midpoint? And that would be a mixture of Gaussians. It would be this red mixture of Gaussians. Or you could say, what is their Wasserstein midpoint? So what is the distribution which in the Wasserstein sense is equidistant from those two? And that would turn out to be a Gaussian in the middle. So, and it has this nice thing that somehow it preserves the shape. And so if you think about the line joining one of the distributions to the other, it would just be a Gaussian that went slowly from the left to the right. Whereas the Euclidean thing would be, I don't know, a bump that started like this, and then it would always be two bumps and then go up. So there's some sense in which if you're taking the midpoint of some Gaussians, you would always end up with a Gaussian in the Wasserstein. Everyone okay so far? Good. So you should just think of it as it's a nice distance. Okay, so as a result of the fact that this is a nice distance, there are many statistical applications of the optimal transport framework, and they all revolve in some ways around either attractive properties of the Wasserstein distance, or they rely heavily on this nice fact that we don't just get a distance, you also get a map to transport samples from one distribution to another, right? So, and okay, so I'll give you just a list of applications so you can use it to design two sample tests. You can use it in some very nice way to define a multivariate analog of quantiles. So you can think of mapping some distribution to the uniform and use that mapping in order to define quantiles. So this is a very nice application of optimal transport. You can use it in domain adaptation where you're trying to make predictions under a different distribution. Then it makes sense to have a map to go from source distribution to target distribution, and use it in various other cases as well. And I'll also just briefly mention that there are lots of connections between optimal transport and areas of statistics. So in particular, concentration of measure, there's some very deep connections between optimal transport and concentration of measure. There's connections which arise in mixture models where the sort of optimal transport distance between mixing measures is related to the Hellinger distance between distributions. It comes up a lot in the design of sampling or Langemann algorithms and so on. Okay, questions? Good. So now finally we'll get to the meat of the talk. So I'll tell you about the first problem that we looked at, which is this problem of estimating optimal transport maps. So here's the setting. We're going to think about the following statistical question. I give you samples from a distribution P and some samples Y1 through Yn from a different distribution Q. And let T0 be the optimal transport map from P to Q. So now we're just asking the statistical question. Construct an estimate T hat of this quantity T0. So there's some population quantity T0 that you don't have a handle on. You get samples from the two distributions and you'd like to estimate it. So construct one that has small risk. So that is the expected distance between T hat and T0 in the squared sense is small. Okay, so this is the statistical question that we'll think about for a while. So this is the problem of estimating the optimal transport map. So in pure math, you often think of the case where I hand you the two distributions. In statistics, we often think about cases where rather than give you the distributions themselves, I'm going to give you some samples from them. And very broadly, this is the area of statistical optimal transport. It focuses on estimation of objects like the Wasserstein distance of the transport map or barycenters. These are all objects that are in the OT framework, but you focus on their estimation and inference for those objects when you're given samples. Good. So maybe the first question one should ask is, how does one design an estimator for the optimal transport map? It seems like a kind of unwieldy object. Turns out that there are some fairly natural estimators. So the first kind of estimator that you should think about is what are called empirical estimators. So what is an empirical estimator? It says you do the following operation. I've handed you samples. You can compute the optimal coupling between these samples. So the optimal map of going from the X sample, say, to the Y samples. In this case, maybe it looks like something. So given these X samples and Y samples, I can figure out what is the minimum cost way of matching the X samples to the Y samples. And then in order to define a map, I need my map to be defined everywhere. So I need to find some way to extend it. The most natural way to extend is to use nearest neighbors. So if I give you a point X, you find its nearest neighbor in your sample, and you go wherever that sample got matched. So this is a way of constructing an estimate for the map. Right, okay, so you just compute what's called the in-sample coupling, and then you extend it by the nearest neighbors. And just as a side note, you can run some fairly quick algorithms to compute the matching. You can even approximate it. You might lose some statistical efficiency, but you should think of this as a somewhat easy problem to solve. Given n samples from X and n samples from Y, computing a matching is perhaps not that difficult. Okay, questions? Another class of estimators are what are called plug-in estimators. These are smooth estimators. So maybe the basic intuition is that the empirical estimator, it's based on this nearest neighbors idea. It may not exploit somehow the smoothness of P and Q. If I tell you those distributions are smooth in the usual non-parametric sense, your estimator maybe cannot take advantage of this. So more generally, you could think of the plug-in principle. The plug-in principle just says compute some density estimate P hat, some other density estimate Q hat. And you now try to say, my estimate for the optimal transport map will be the optimal transport map between these two density estimates. Okay, so you can imagine in your head, you computed a kernel density estimate for P, a kernel density estimate for Q, and then you just figured out what is the optimal map between them. This is not as easy a question, but you can imagine trying to approximate this either by some sort of discretization or by sampling P hat and Q hat many times. But for us, okay, it's something that one can do. It's maybe not the world's most practical way of computing a map, but one can still ask. It's a very simple, intuitive to define estimator. One can still ask how well does it do in some statistics. Everyone good so far? Okay, so this is roughly the picture you should have in mind. Someone did exactly this. In this case, this you could have imagined was a kernel density estimate and a kernel density estimate, and this plot on the right was computed by discretizing each of these distributions, either by resampling or by, in this case, by a grid, and then computing the map on that grid. Okay. Both the empirical estimator and the smooth estimator, they're very natural in some sense. And they'll turn out that they've never been analyzed, and there's a reason for it. They're kind of hard to analyze in practice, hard to analyze in theory. And so I'll tell you a little bit about how we did analyze them eventually. Okay. So before I tell you that, I have to tell you a little bit about what the setting is and what the kind of rates are that we might hope for. Okay, so here's the setting. So this now comes from a paper of Jan Christian Hutter and Philippe Rigolet. They were the ones who maybe sort of formally said this is the problem of optimal transport map estimation, and here are some statistical minimax rates that one might hope for. So let me tell you what they did. They said, suppose the map itself is smooth, right? So it's somehow alpha Holder. And suppose that now we'll start making lots of assumptions. Some of them you can get rid of, some of them are probably hard to. Assume that your densities are compactly supported, they have nicely behaved densities. And maybe a key assumption is that this Brenier potential, so the Brenier potential is P0, we'll now make this assumption that it's smooth and strongly convex. Okay, so for some intuition, you should think about it as saying there's some sense in which the transport map is close to a translation type map, right? So it's close to something that's like the identity. If that doesn't make sense, then just ignore it. It's just saying this function phi, the Brenier potential, whose gradient is the transport map, its gradient has to be well behaved in the following sense. Okay, suppose you made all of those assumptions, then what can you say? Then Hutter and Rigolet characterize the minimax rate. They just said that the risk of the best possible transport map estimator here looks like, okay, it looks like n to the minus 2 alpha over 2 alpha minus 1 plus t. If you're used to staring at non-parametric rates, then you might think that the familiar rate for some estimating an alpha smooth object should look like 2 alpha over 2 alpha plus t. And so there's some sense in which you are now getting a slightly faster rate. And this has lots of nice implications. One of the implications is that this rate can sometimes, at least in low dimensions, it will actually be parametric. So if t is less than 4 or something like that and alpha is big enough, then this rate will be parametric. So this never happens in non-parametrics. And if there wasn't an alpha minus 1 here, you would always be getting this non-parametric rate. But here, in some cases, you can actually get parametric rates. And we will squint at this rate a little bit more. I'll tell you where it comes from and how to think about it at some point. But maybe the first order takeaway should be, looks kind of like a non-parametric rate, but it's slightly faster. And that slightly faster has some meaningful implications. Everyone okay so far? Maybe for now, I'll tell you one way of thinking about where this rate comes from. This is maybe not the most transparent way to think about it. So if it doesn't make sense, just ignore it. So remember this change of variables formula. It said something like P of x over Q of P of x looks like the determinant of the gradient of the transport map. So you should imagine in your head, you're sampling something like the distribution P. So you're in some word observing the gradient of the transport map. And what you would like to do is estimate the transport map. So you want to estimate the antiderivative of the thing you're observing. And the thing you're observing is an alpha minus 1 smooth object. And if you knew how these rates work, then you would expect a rate that looked like this from this intuition. You're somehow observing the gradient of the map, and what you want is the map. Great. So let's keep going. So what is the drawback of what they did? So first, let me tell you what is the nice thing. How did they compute their estimator? They did not use one of these nice plugin estimators. What they did instead was they solved for the Brenier potential directly by deriving so Kantorovich had an LP, you can derive its dual, and then you can solve the dual. And then you can use that potential and say whatever its gradient is, that is your estimate of the transport. And so that's roughly what they did. What is kind of nice about what they did is that they showed that even though this is a linear programs are notoriously unstable. Right? So linear programs have this property that the optimum is always at some vertex. So if you perturb it a little bit, the optimum can jump around. But what they showed was under this curvature assumption, it actually behaves kind of like a quadratic program, something like least squares. And you can analyze it using similar techniques. Well, what is the main drawback? The main drawback of what they did was that the estimator that they wrote down this is a quote from their paper, it's just not implementable because you should think of it as a proof of concept estimator. It's defined as you optimize over the coefficients of a truncated series estimator and so on. There's like a lot of tuning parameters in it. And as they point out, it's probably not even, it involves computing the convex conjugate of a function inside it. It's not practical in any reasonable sense. And so what we'd like to do is just go back to these natural looking estimators that we thought about and say, can we prove similar looking things about it? And how do we do this? Okay, so let me tell you the main result. So this is from our paper. Suppose that these distributions are alpha minus 1 smooth. The map is alpha smooth. This will somehow, these scales will make sense. Then you can both analyze the nearest neighbor estimator. The nearest neighbor estimator will achieve the correct rate when alpha is 1. And you can also analyze a kernel smooth estimator or a wavelet estimator, so these smooth estimators, and they will achieve exactly the minimax rate. And so this is the same rate that Hutter and Rigollet said was the minimax rate. So the basic takeaway is that empirical estimator and the smooth estimator achieve the minimax rates. Okay, so and maybe we should take away that the nearest neighbor estimator is only optimal when alpha is 1. The smooth estimators are optimal in general. Everyone good so far? Okay, so now let me tell you what we did. I think there's something kind of intuitive and nice about it. So perhaps not difficult to follow. So our estimator is just a plug-in estimator. So you should think about the problem as the following. I compute P hat, which is some sort of OD map, say between P hat and Q hat. And the target, the thing that you want, is the OD map between some distributions P and Q. And what we'd like to say is somehow P hat and T0 are close. Right? So you might intuitively hope that if P hat is close to P and Q hat is close to Q and the world is nice in some way, that then P hat and T0 would in fact be close. Right? So maybe one question one should ask is, okay, what is the sense in which I need P hat and P to be close and Q hat and Q to be close? We have to answer that question. But okay, the basic idea is going to be to try to prove what are called stability maps. So when our OT, we want to understand when our OT maps stable to perturbations of their arguments. And stable to perturbations of their arguments is a okay. So let me tell you what we showed. And this will somehow answer this question. So it basically says, suppose I let P hat and Q hat be some estimators, they're kind of nice, and you have all those conditions that we already had. Then what it tells you is that the expected distance between T hat and T0, this is kind of like the risk that you wanted to bound. You can ignore for now the term in the middle, is upper bounded by the Wasserstein distance between P hat and P and Q hat and Q. So what this is telling you is that transport maps are in fact stable to perturbations of their arguments, as long as those perturbations are small as measured by the Wasserstein distance. And if you care, we'll come back to this at some point. The thing in the middle, you should think of as a first order Taylor expansion of the Wasserstein distance function, right? So it's somehow saying, this is like a linearization. This is the Wasserstein distance at P hat Q hat minus its value at PQ plus some first order term. And this is the thing on the right, you should think of as the quadratic remainder. So for now, the thing you should take away is just transport maps are stable if you perturb their arguments in the Wasserstein sense.
And the lambda has to do with the smoothness of the.
Brenier potential.
Yeah,
exactly. So you should think of the Brenier potential being smooth and strongly convex as the thing that drives all of this. It is the thing that's giving this. So perturbations come from curvatures. So that is, you want something to be curved in the appropriate sense so that if I move a little bit, things are still stable. And the curvature of the Brenier potential is exactly what drives the curvature.
And that was the property of P and Q.
It's yeah, so that is correct. That is, if maybe the easiest case is when P is a translation of Q, then the map will be just a constant addition, and then the Hessian will be a constant. So there's a case, so that's the nicest case, which is translation. And so you should think of this as saying P and Q are close to a translation of each other in some appropriate sense. But yes, it's a property of P and Q that determines what the Brenier potential is and determines its curvature. Okay, good. This leads us to a different question now. It says, in order to understand these rates that we wanted, what we actually have to understand is how well can we estimate distributions under the Wasserstein law. Seems like that is the thing that drives our rates of convergence. So we visit this part. It's just saying there's some linearization of the Wasserstein distance under the hood. We'll come back to that. Okay, so now let's ask this question, which is, I think, interesting in its own right. Suppose that I give you some distribution and smooth in some sense. You can ask, how well can you estimate this distribution under the Wasserstein laws? We're all familiar with trying to estimate densities in, say, the squared laws or things like that, or the KL or TB, some more different looking metrics. And now we're just asking, is it easier or harder, or how well can we estimate distributions under the Wasserstein laws? Okay, so in order to understand the answer to the question, we have to get some handle on how the Wasserstein laws behaves. And this is maybe one intuitive way of thinking about it. So suppose you have P hat and P, they're kind of nicely behaved densities, then it turns out that you can at least approximately think of the Wasserstein distance as the distance between P hat and P as measured by something called an inverse Sobolev norm. I'll tell you what this is in a second, and it will maybe give you some intuition about what the Wasserstein distance is. So first, let me remind you what a Sobolev norm is. So if I said the Sobolev norm of a function is you just integrate the derivative of that function and square it and integrate it. That's the squared Sobolev norm. And so now I'm saying, no, don't look at the Sobolev norm, but look at the inverse Sobolev norm. This is the dual to the Sobolev norm. And what does that mean? It just means you look at the distance between p hat and p. It's now an integral probability metric. So what does that mean? I'm going to look at the distance as measured according to a whole bunch of test functions, and those test functions are all the Sobolev functions. So you take all these smooth functions and you say, okay, according to them, how far are p hat and p? So it's an integral probability metric. If you've seen things like the total variation or the MMD, you've seen expressions that look like this before. They measure distances between distributions by integrating them against a whole bunch of test functions. These test functions will test if the distance is big or small. And you should think of the Wasserstein distance as basically like an integral probability metric, but the test functions are smooth in this sense. They're smooth in the sense that they have small Sobolev numbers. Okay, so rather than look at the L2 distance or so that maybe the TP distance would say, look at p hat minus p against all bounded functions. Those functions can be very non-smooth. This is saying do something slightly nicer. Look at the distance between p hat and p as measured according to all smooth functions. And you've probably seen a similar looking expression for the W1 distance. So the W1 distance, there's an exact duality which will say it's the integral of p hat minus p against Lipschitz functions. And this is a similar looking expression for the W2 distance. Everyone okay with this? Just think of the Wasserstein loss as a slightly more forgiving loss than the usual density estimation. And okay, if you translate all of this into rates, this will explain why you're getting slightly faster rates for transport map estimation. It's because Wasserstein density estimation is a little bit easier than regular density estimation. Is everyone okay so far? Then let's move on and now talk about a slightly different problem. So this is one of estimating the Wasserstein distance. And it'll turn out the same story. The stability bounds will be kind of useful. So here's the question. Suppose I observe some samples x1 through xn from a distribution T and some samples y1 through yn from a distribution T. The question is, can you now give me a reasonable estimate? So we're forgetting about transport maps now. We're just asking about the distance. How well can you estimate this distance, which is the Wasserstein distance between the two distributions? And maybe as a secondary question, can you construct a confidence interval? Everyone okay with the question?
So you have to distribute the number of answers by the same.
Yeah, so they don't have to be the same in general. Like you will pay for the worst of the two in some sense everywhere. So at least from the point of rates, it's probably nicer to think of the case when they're the same. Otherwise, it's effectively as bad as throwing away a bunch of samples. So yeah, it's a good question. There isn't a clear sense in which even knowing one of these distributions doesn't make this problem much easier. So let's back up and think about why is this an interesting problem. So this is an example of what in statistics we call functional estimation problems. They're kind of interesting for the following reason. So I'm giving you all of these samples. There are these complicated distributions under the hood, but the quantity that I'm interested in is just this one-dimensional quantity, which is the Wasserstein distance. So I don't care if you can estimate the whole distribution or not. It's irrelevant to me. What I care about is just, can you tell me exactly what the Wasserstein distance is? And when can you do this at, say, parametric rates? Since it's a single one-dimensional number, you should expect to get 1/n rates if you were lucky. Everyone okay with this? So you should think of these as somehow different questions from the usual density estimation or function estimation questions. They're functional estimation questions. I just want a single number here. Okay. And this is very similar in spirit to classical work, for instance, by Peter Bickel and Jakob Retow, and many others who study the estimation of functionals of densities. And this you can view in that way. It's a two-sample functional of a density. It's not a particularly nice looking one. Okay. So maybe one thing that one can do is to write down what is called the plug-in estimate. So the plug-in estimate is the thing that one would first think about here, which is I need to estimate the Wasserstein distance between P and Q. I'll construct some estimate P hat and Q hat. and I will construct the Wasserstein. My estimate of the distance will be the distance between these density estimates. So this is called the plug-in estimate. And what we showed essentially was the following thing. If you have enough smoothness, the alpha is at least something which is quite large. You think of it as quite large, d over 2 minus 1. So you have sufficient smoothness. Then you can use this plug-in estimator, and this plug-in estimator will be asymptotically unbiased and semi-parametrically efficient. So what's going on is it's saying that at least if you have this amount of smoothness, then you can estimate the Wasserstein distance exactly. It'll be as hard as estimating a single number. So you can quantify exactly what the variance is, and it'll be the right variance. Everyone good with this? Okay. So let me try to explain how this comes about. But just for a second, let me just pause here. It's just saying that there are cases where this plug-in estimator is usually often kind of biased. Often we need some sort of debiasing to try to debias the plug-in estimator, but this is a setting where the plug-in estimator itself directly is efficient at estimating the distance, at least if you have enough smoothness. So let me give you some information about where this is coming from. So now we'll use the part of the stability bound that I kind of asked you to ignore before. So the stability bound in the middle had this term, which was the distance between the plug-in estimate of the Wasserstein distance and the true Wasserstein distance. After you do some first order correction is second order, right? So this is what our bound told us. So imagine you're in a setting where somehow this term is asymptotically negligible, kind of small. Then you can say that whatever it is, this error between these two is governed by this quantity over here. And this quantity, okay, if pi hat was just a empirical estimator for some reason, it's not some smooth estimator, but if it was some empirical thing, then this would be the average minus the expected value of some function. And that thing, you know, should have a CLP. And so essentially what we show is that under those smoothness assumptions, you can ignore this term. And even though this pi hat is constructed from some kernel density estimate, it's not exactly an average minus an expected value, but it's a slightly smooth version of that object. And even that will satisfy a central limit theorem. And so basically what we get is that this root n times this difference, this plug-in estimator, is asymptotically efficient. So it has an ortho distribution. Everyone okay? Yeah.
So at the risk of oversimplifying, could I interpret this as saying that there's no need to be biased because the optimization problem is something you can solve exactly for a particular p hat and q hat? No?
No. There's some sense in which what it's saying is that the reason you don't need to debias is because there is some setting, some sufficient smoothness where this thing, which is expectedly the bias, can be small. It's just driven to zero. It has nothing to do with the fact that you're optimally coupling these. It's not that some first order term goes away because you're at a maxima or a minima or something like that. That's not what's going on. It's just saying that because this problem, somewhere I said that you get this alpha to alpha minus 1, and so there's some regime where you get parametric rates for, like, say, the transport map. That's what's kicking in here. So there's some regime where if with enough smoothness, things can be done parametrically, and it's because this Wasserstein distance is slightly nicer behaved than the squared distance. I will try again at some point, but yeah, I'll try to do it again after the talk. Okay, so let me tell you something else, which is also true, and it's an older result. There's a very nice result of Del Valle and Lopez, and what they show is that there's a sense in which the CLT kind of holds for the plug-in estimator far more generally than the setting in which we did it. So what did they show? They showed the following statement. If you just looked at the squared distance between the empirical measures Pn and Qn, and you subtracted off, you centered it at the expectation of this quantity, then if you scaled it by square root n, you would essentially always have a normal limit. Okay? But the problem is that this central limit theorem is not so useful for constructing a confidence interval for the Wasserstein distance. And the reason it's not so useful is because it's centered at some quantity that we don't understand, right? So that it's centered at something which is roughly the bias of your estimator. But what their result tells you is, okay, if you're willing to tolerate this weird centering, then you don't need any assumptions. You don't need that much smoothness. You don't need that much to happen. You will always get root n rate CLPs. Okay. And so basically all we did was to say that there's some sense in which if you have enough smoothness, you can replace this centering by a useful centering, which is the actual Wasserstein distance. You would like your estimator to be centered at the truth, not centered at its expectation. Okay? Okay, so maybe one other higher level takeaway is that if you think about the empirical Wasserstein distance, it has a lot of bias and very little variance. The variance is essentially always kind of negligible, but it's the bias that's the problem. And okay, in some cases, you might be able to ignore the bias if these kinds of stability things work. Okay. Good. So the last thing that I'll talk about is just a slightly different problem. I won't tell you anything about proofs. I'll just tell you a result, which is another very natural question that you might ask is to do inference for the optimal transport map. Right? So I told you something about the rates at which you can estimate it. I can ask you to do the following thing, which is construct a confidence interval for P0 of X. So this is some vector valued quantity. It's telling you the value of the map at some point. And I can ask to tell me how it fluctuates if I say resample the distribution. So what is the distribution of T hat around P0? Okay, and so this is from some recent paper that we wrote. And here you will need a lot more assumptions. The math is a lot harder, and I'll try to explain why it's much harder. But here's what happens. Suppose that P and Q are alpha minus 1 holder, we're in exactly the same setting. And you use the KDE-based estimator with some slightly lower than the optimal bandwidth. So what is going on in these problems? Okay, if you think about non-parametric regression and you wanted to construct a confidence interval, you would need to do something which is called undersmoothing. So if you balance bias and variance, then you're in some trouble because you can get some handle on the variance, but the bias can be quite large. So what you need to do in, say, non-parametric regression in order to construct a confidence interval is that you need to take a bandwidth that's slightly smaller than the optimal bandwidth so that the variance dominates, and then you can construct a confidence band. Right? So something similar happens here. If you're trying to estimate a transport map, you can use this KDE type plugin estimator, but you need to pick a bandwidth that's slightly smaller than the correct bandwidth. And when you do so, and you scale things the correct way, you will get some centered quantity. So that is, you can now, and the variance is easy to estimate, so you can construct a confidence interval. What is maybe the most dissatisfying part of this is that all of this only works when P and Q are supported on a torus. So that is, you have to be on some nice looking domain which has no boundaries. And otherwise, we don't have any idea how to do most of these things. Around okay with this, but okay, at least in some limited settings, you can undersmoothing, which is a standard idea in non-parametric regression, also works to give you confidence bands for the transport. Questions about the result? And maybe this is one of the first results that characterizes these pointwise fluctuations of the transport map. It's useful. So you can imagine in your head, there's this transport map object, and I'd like to put some sort of band around it to say, okay, I have some reasonable confidence that in the population, these points get moved to these points. And so this is what this kind of result is helping you do. I will not say how this is done, but roughly what you have to do is to take that partial differential equation that I wrote down with change of variables formula, it's called the Monge-Ampere equation, and then you try to linearize it. It's a non-linear partial differential equation. You can try to convert it to a linear one by some approximations, and then try to study the solution of that linear PDE. Turns out to be quite some work. This program itself comes from people in pure probability have often cared about the case when P and Q are uniform, and this is then called the Euclidean matching problem, and then you would like to understand the case when just these two. And in this case, people have tried very hard to understand the asymptotics of these transport maps. And we basically try to extend their ideas to the case when you have more than 2 dimensions under some appropriate smoothness. Yeah.
In this one, you'll only get pointwise confidence band. Like it's not a band the map, but it's just for each X you can get some.
Yeah, so if you can prove something which is like a negative result that says you view this as a process and you say, does the process converge? The
Yeah.
process does not converge. So you are correct.
So there's a negative result.
Yeah, you can show that the process will not converge, but that's not what you need. What you maybe need is something like the L infinity norm of that process has to converge. That might actually be true, but we don't really know how to prove it. So there is some hope for a more useful positive result. This is a initial positive result. Yeah, that's a very good question. There's- I'll tell you this, but there are lots of open questions in general. So let me just summarize quickly. So I told you about three different things. I'll just remind you what they were and tell you what the main takeaways were. I told you about this problem of estimating transport maps. And maybe the first order takeaway is just under natural smoothness assumptions, there are these natural plug-in type estimators, which are in fact minimax optimal. And maybe the key idea that was that we developed these new notions of stability bounds, which say, okay, if I perturb the arguments, how much does the optimal transport map change? And that helped us analyze these transport map estimator plugins. Then we talked about a little bit about estimating the Wasserstein distance. And here maybe the takeaway is at least if you have enough smoothness, you can get a CLT that is usefully centered at the correct population counterpart. And then finally, I told you very briefly about pointwise inference for the map. And here, importantly, everything's done over some weird domain that seems hard to get around most of these regularity conditions. But essentially what the result says is that you can characterize the fluctuations of t hat minus t0, at least at a fixed x. And you can say, okay, they look normal, provided you under smooth in the right. Let's just say at a high level, we've only begun to scratch the surface. As you can see, these are fairly rudimentary, basic sounding questions, and it seems like we don't really, even for these, have a good answer yet. There are lots of questions that you can ask, even locally within the context of what I told you. An important question would be to try to do transport map estimation without this whole curvature of the Brenier potential thing. We'd like to do inference outside of the torus. You would like to actually rigorously construct confidence bands, not just pointwise inference. And maybe just more broadly, our understanding of statistical questions in optimal transport are kind of weak, and we have very few results so far in this area, and it would be nice for more people to get excited and interested in this. There are lots of methodological uses of optimal transport, and we need to catch up a little bit. Okay, so maybe the one level takeaway is just that OT tools are very robust in some ways. That's why people like using them. The inferential tools are still very brittle. Like answering even basic questions requires you to understand some optimization problems. Our optimization problem is quite complicated. And so maybe finally, again, it's an exciting area. It's not, if you are bored of using Fano's inequality to prove lower bounds and something else, this area has some set of questions that require ideas that are quite different. And so from that perspective, maybe it's quite interesting. Okay, I'll stop here.
Can you go back to the asymptotic normality result?
Yeah.
Yeah, I'm thinking about this result. So if I, here is for even each given axis. So this axis is deterministic, right?
Yeah.
So if I learn T hat already, and I want to apply it to a new data set, I wonder if you can comment on what can I say about after applying optimal transport. Because then T0 X, here X random variable will have the same distribution as Y, right? And T hat X, I guess for each given X is asymptotically normal. But if I have a data set, what can I say about the transformation of the data set after applying T hat?
I think there's some sense in which you should think of the estimation results as giving you some answer. No, this result doesn't tell you anything about that, but maybe a question that one can ask is, okay, if the X here is random and drawn from this distribution, can I say something about how far on average these things are? But that is roughly the estimation risk that we try to bound. If you want a more point-wise answer, maybe you want a uniform version of this statement. That is for all, you could hope that for every X, something like the statement is true. So I don't know if I gave you a good answer. If you care about some average case version of this, then maybe the estimation risk kind of tells you something about that. If
But
you
on the
cared
same
about,
data, I guess, like in sample.
oh, you want an
sense.
in-sample, okay.
No, I guess I try to understand whether like the risk bound that you provided is for in sample also.
It's out of sample. So
Okay.
it's somewhere, some of them. Yeah, the risk itself is an expectation over the true distribution. So it's an out of sample.
Sure.
But yeah. So this risk is measuring somehow out of sample, how good is your map in the squares.
Mhm. So maybe I missed it. So this R T hat T0. Do you have a bound for this? I
Yes.
apologize if I missed it.
No. It says that this is the thing that that Hooter and Riggle gave minimax rates for, and this is the thing that we
Oh, right,
also
yeah.
factorize. So somehow, when we say our plugin estimator gets some rate, it effectively, in this sense, achieves this rate.
Okay, got it. Thank you.
So can I ask more about lambda? So, and this is a good slide actually for that. So, is it correct? Can you give intuition, like what would be a case where this gets violated? Like, because it's not smooth in P and Q, right? It's rather like the transport between P and Q being unsmooth.
Yeah, so that's correct. Yeah, so I guess you should ask which direction of it. So this is the gradient of the transport map. So if you construct, for instance, examples where, okay, your density gets very small, so you have kind of like a disjoint support, then the transport map at some point will have to, like something in the middle will have to go in one of two directions, and then there'll be like a sharp transition. And so you're kind of disallowing things like that. This direction of it is kind of forcing that the transport map is smooth. And so you are basically disallowing some weird discontinuities.
And then the other direction is saying that it can't change. It can't be constant.
Correct. That is correct. That's right. So that is, you should imagine again, in some cases where, again, if you have low density, you can imagine that the transport map will be indifferent to where a whole bunch of points go. And then it'll be very hard to say exactly, to relate the transport map error to some global error, which we did. Right? So then you'll have to deal with those regions. So it is saying what you said, the transport map can't be flat in some sense anywhere. But that will basically happen if you have regions of low density where the transport map is kind of indifferent to where all of these points are. And that can't happen. Not the easiest condition to get your head around, but I think the idea is somehow this condition gives you some handle on this risk in terms of quantities that we understand. But it is a curvature of the optimization problem that one is solving in optimal transport.
Thank you for the very exciting talk. I want to ask like a question which is more on like application of
Okay.
the statistics. Right, so like nowadays that like the generative AI stuff is super popular, and sometimes they like try to. So suppose like we have to like DALL-E, which can generate some like pictures based on the prompt, and then now I have like say 100 pictures generated by 2 DALL-Es, and then is there a way to evaluate which like generative AI model is better? I think sometimes they try to characterize what's the distance between the distribution of the generated pictures to the true pictures, like the pictures people take in the real world. And then sometimes they pick like what is scientific distance, sometimes they pick the divergence between the distributions. And I wonder, like, do you think like according to your analysis, the method scientific distance can give a sensible measurement the distributions of image?
Yeah, so I think you kind of answered the question somehow, but yeah, so you could use the Wasserstein distance between images, but that would probably be a very high dimensional thing, and so it may not be so sensible given samples like pictures are all going to be quite kind of far apart from each other, so the Wasserstein distance will be kind of inflated. So maybe one can try to define versions of the Wasserstein distance that behave better in high dimensional problems, and so people do this. So you can think of like the entropic Wasserstein, like regularize this distance in some way or smooth this distance in some way. And those are things that people use on high dimensional objects. The other is maybe you shouldn't use it in pixel space, but use it on some lower dimensional representation somewhere in the middle of your generative model. And then maybe then you can get some more reasonable handle. But I think it is a sensible way to compare distributions over images. It's just you have to be careful of the fact that they're high dimensional. And so you need to account for this.
Okay. One final question about the connection with the applications. So you mentioned at the beginning there are several statistical problems that optimal transfer is relevant for.
Yeah.
How do you connect the problem, the statistical problem you're trying to solve with the type of guarantee you're trying to, with the type of theoretical property you're trying to get for the optimal transport? Like, is there a type of theoretical property that is kind of going to be useful for many types of applications? So would in some applications be sufficient to get maybe a simpler type of property for optimal transport?
Yeah, so it's a good question. So I don't know, maybe it depends really on the application, but let me just try to pick one. So say you looked at two sample tests. So what do people do with two sample tests? Basically, it's the obvious thing. I give you samples from P and samples from Q, and you want to know is P the same as Q? You can measure the Wasserstein distance between Pn and Qn. This is a very natural test statistic. But in order to calibrate your test, you probably need to say, okay, well, how does that behave under the null? And if you want to say something about the power of that test, you would like to say, okay, P and Q are different in a certain sense, then the empirical Wasserstein is a good estimate of the true Wasserstein. So in that kind of application, I would say, okay, the two basic questions that one needs to understand how useful Wasserstein distance is in two sample testing is you need to understand the distribution of your estimate of the distance, and you need to understand how it behaves when P and Q are problems. So you need to understand how well your estimate of the distance approximates the distance. And so so I would argue that the kind of problems that I talked about are somehow, if you wanted to go deeper in any of these applications, you would need to understand those kinds of theory questions, which are just given samples, how well can you estimate various objects? They somewhere drive how well you would do in any of these applications. That answers the question.
Yes, I mean, I guess based on the specific test statistic you're using for two sample tests, for example, that would tell you what is the quantity that you're actually interested in studying, right? Like whether it's like some normal optimal transport map or something like that, right?
Yeah, so I'm saying that in this case, it's not that complicated. It is just the Wasserstein distance.
That's just okay.
But you are correct, which is, I don't know, if you used one of these applications where the map was actually important, then maybe you don't need point-wise control. Maybe you don't even need L2 control. Maybe you just need some weaker control on the map, and that would suffice for some downstream guarantee. But yeah, one would have to dig into these applications.
Okay, I think in the interest of time, let's thank Shiva for a great talk.